All right, so if you were going through the book at home, you probably noticed that we skipped around a little bit. The equation part was just one little section in the middle of chapter 7, but I thought that fit best with what we were doing before we go into all the math stuff. So we're gonna go into the math stuff and learn how to do some calculations with these types of equations. And to do that, we need to talk about the famous mole. Has anybody heard about this before? The term associated with chemistry, mole? No? Okay, good. It'll be new. Some people, yeah. All right. The problem with what we just did with all the balancing equations is that this sort of assumes that we can count up molecules. So if we want to, let's say, do this reaction right here. In order for everything to be in balance properly, we need 2 of these molecules for every 3 of these. That's what the equation tells us. 4 of these for every 5 of these, 2 of these for every 3 of these. But on the molecular scale, like these tiny things, you can't do that. There's no molecular tweezers that you can pick out from your jar and put these things together. So we need a different way of counting these things. A different way from just counting them one by one. All right, so here's an example. Has anybody ever done the giant jar full of jelly beans and you have to guess how many of them are in there? Has anybody ever won that? No? Not lucky? Yeah? What'd you win? Was it like really big?
Yeah.
How long did it take you to eat them? Just one good night?
Yeah.
Yeah. Okay, anybody else? So you know, you've seen, but you know the idea, right? You fill a giant thing of jelly beans. Has anybody ever seen like a really giant one, like a floor-standing, huge thing? Yeah, I saw one at a toy store the other day. So even if it's not that big, how do you think they figure out who wins? Do you think like some poor employee has to count jelly beans, count them all in the giant thing? I don't think so. I don't think they would do it that way. What would be another way to count up a giant jar full of jelly beans without actually counting the individual pieces?
Like in the pharmacy?
Okay. I don't know a lot of candy places that have jelly bean counting machines, but that would work. Yeah, maybe. You could weigh it, right? So there's a way that you can count things by weighing them. How do you count things by weighing them? How would that work?
You see what 1 unit weighs, and then just multiply it or divide it by whatever that weighs.
Yeah, exactly. So does everybody kind of see the idea of that? So if you have a whole giant thing of jelly beans, you could weigh 1 jelly bean, and then you could weigh the whole thing of jelly beans. Divide those 2 numbers, and you know how many there were. Because if each jelly bean weighs a certain amount, assuming they're standardized, then you can figure that out that way by dividing. So that's essentially what we do with molecules with really small things. We can't count them out individually. So instead we weigh them out, and we use this number called the mole to translate from the molecular scale, which is tiny, to the scale that we can understand, that we can deal with. So, for example, we can say that carbon, 1 carbon atom, weighs about 12 AMU. Remember that unit, atomic mass units? So that's how much an actual carbon atom weighs. If we convert that to kilograms or grams, it's a tiny, 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 tiny number. So we say AMUs instead. So we're not going to count 1 carbon atom. We're not even going to weigh 1 carbon atom. But if we weighed a bunch of carbon atoms, and we knew how much it was and how much 1 carbon atom was, we could figure this out. So the way that we do this is we say 1 carbon atom weighs about 12 atomic mass units. 6.02 times 10 to the 23rd carbon atoms. That's a lot of carbon atoms. weighs 12 grams. So look what we did there. We converted from the tiny atomic scale of weight that we can't really do anything with to now our actual human scale of weight that we can. 12 grams is like, you know, like a small handful of carbon or something like that. So we can do that. We can weigh that out on a scale. So we can count carbon atoms as long as we can count a whole bunch of them. And so this number, this 6.02 times 10 to the 23rd, this huge number, if you don't know scientific notation, the 10 times 10 to the 23rd means basically a 6 with 23 zeros behind it. So it's just an unimaginably large number. Like we can't, there's stuff in your book about like how many pennies that would be, you know, that would like cover the earth a bunch of times and stuff. It's just a ridiculous number. We can't understand it. But that's because atoms are so small, so ridiculously small that we can't understand their size even. So this is how we transfer between the two. And so we say things like 1 mole of carbon atoms, we're going to define that term mole, is that huge number of carbon atoms. So importantly here, that number isn't a unit, it's just a number. It's a name for a number. It's the same as saying 1 dozen carbon atoms is how many? Everybody knows that one, right? 12. Those two equations are saying the same thing, just with different numbers. It's a way of defining a quantity, a word to stand in for a quantity. We could say dozen, we could say mole. Different numbers, but otherwise it works the same way. Okay. So the other advantage of this then is we can kind of talk about this as though it were a unit. So if you have a dozen donuts, you can also have 2 dozen, you can have 3 dozen, you can have half a dozen, you can have 0.3 dozen, you know, you have to cut up some donuts, but something like that. So you could cut up your dozen, you could have more dozens. Should have brought some donuts, I'm hungry. But you can do the same thing with moles. So we can talk about 1 mole of carbon atoms, 2 moles, half a mole. And going back to these equations, we can talk about these numbers in terms of moles instead of in terms of molecules. So just like the equation tells us that 2 of these molecules reacts with 3 of these molecules, we can say 2 moles of this react with 3 moles of that. And that's something we can actually measure in the lab and understand in the lab. So it tells us some things about these ratios. The other nice thing about that is we can define some quantities to use with this mole that help us do all these types of calculations. So we can talk about what we call the molar mass, which is sometimes called the molecular weight. And we can find the molar mass by adding up the molar masses of each constituent atom. So that red number on the periodic table gives us the molar mass of each atom. So let's define that. So that red number is the molar mass of carbon. We said before it was an average, that like an individual carbon atom would be 12 or 13 or 14. The number up there is an average of the different masses. So when you have a mole of something, that is fine because there's so many of them, you know, so many ridiculously high number of them. then of course there's going to be lots of 12s, 13s, and 14s in that correct ratio. So we can just use that number as is. A couple different ways we can use it. We can use it like a conversion factor. So we can say 1 mole of C, and the abbreviation for mole is MOL. So we can say 1 mole of C equals 12.011 grams, and we can use as many significant figures as we need depending on what we're doing. We can also use it like a ratio, just like with our other conversion factors. So we can say things like, let's do it this way. There's 12.011 grams of C in 1 mole of C. That's another way we can think about it. And then we can also talk about the molar mass of compounds by adding those things up. So if we want to know the molar mass of CH4O from that equation there, we would add the mass of C, 4 masses of H, because there's 4 H's in the formula. So we would look up at H 1.008. We should really use the same significant figures. Let's fix that. And O, which would be 15.999. Okay, we can add all those up. What's the problem with the calculator? What? Why wouldn't the calculator work? Oh, there is no calculator. Okay, can somebody add that up? That's weird. There's the calculator not work. $32.
32.0416.
So let's go like this. So that tells us there's about 32 grams per mole. So there's this many grams of CH4O per 1 mole of CH4O. And normally, I mean, it depends on the problem, but if you're doing the homework in the book, you'll see that in general, when you're calculating molar mass, we don't need to use quite that many significant figures. So we'll usually round down to the whole number, or maybe 1 or 2 decimal places at the most. If you're doing something really precise, you'd need more, but we can always look those up on the periodic table. So that's how we find the molar mass of an entire compound. So how many grams are in 1 mole of a compound. And the way that we use this then is if we want to know how many moles we need, we can multiply that. Like let's say we needed 2 moles of CH4O. We can multiply 2 by that, and we'd know how much to weigh out for 2 whole moles. So let me give you an example of some calculations that we want to be able to do with this. Type these out so we can see them a little bit better. that one, and then we'll do the carbon atoms are in. So we can figure out things like this. So we want to know a certain amount of grams. Like let's say we are setting up an equation and we're going to actually do the reaction in the lab, which we're going to do next week, I think. This week is like doing the reactions, and then next week is doing more of the calculations. So we want to know how many grams are in 1.5 moles of lithium carbonate so that we can weigh that out in the lab. So first thing we need to know is the molar mass of lithium carbonate. To get that, we need to actually know the formula of lithium carbonate. So what's the formula of lithium carbonate? See if you can put that one together. Because we need a formula so that we can calculate a mass. Yeah, thanks. So Li2CO3. Carbonate's a -2 anion, so we need 2 of the +1 lithiums to balance that out. So just like with the equations, you need to be able to write down formulas from names because we're going to use those ratios to calculate this thing out. So now we calculate the molar mass. We want to know how many grams are in 1 mole of lithium carbonate. So we're going to look at those red numbers on the periodic table and add them up. And just for the purposes of this question, I'm just going to round to whole numbers. So we can say there's 7 for lithium. Then we've got 12 for and we need to multiply that by 2 because there's 2 lithiums. Then 12 for carbon. And then we've got 3 oxygens, which are 16 each. So those 7, 2, and 16 numbers, 7, 12, and 16 numbers we get from the periodic table. The 2 and the 3 we get from the formula. Okay, so we add that up. Let's see, that's going to be 48, 60, 74, I think. So we would say there are 74 grams per mole of lithium carbonate. 74 grams in a mole. And then the question asks, how many grams are in 1.5 moles? So we can treat that just like a conversion problem, just like back in chapter 2. Because the equivalence we just found, the thing we just added up, gives us the number of grams in 1 mole. So then it becomes a simple ratio. We can go 1.5 moles, and we can convert from moles to grams using the molar mass. 74 grams per 1 mole. All right, so that's going to be 111. All right? Okay. Sorry, it's harder when I don't have a calculator. 111 grams of lithium carbonate are going to be in 1.5 moles. So that's one way we can ask the question, talk about how many grams. So we would know then, if we were doing this as a chemical reaction, that we would need to weigh out 111 grams to be able to complete the reaction. So then the other part of my question, how many carbon atoms are in 1.5 moles? So now this time, instead of like a practical thing of how much are we going to weigh out, we just want to know how many actual atoms are in that much. Because remember, this is accounting. So we still need the formula. the formula is still Li2CO3. And the reason we need that formula is because it tells us how many carbon atoms there are per unit of lithium carbonate. So if you had one, we can't really say it's a molecule because it's not really a molecule, but if you had one piece of lithium carbonate, one thing, you'd have 2 lithium atoms, a carbon atom, and 3 oxygen atoms, right? That's what the formula tells you. So if you have a mole, 1 mole of lithium atoms, or I'm sorry, of lithium carbonate, how many carbon atoms do you have? Or would you have? Remember that it's just like counting. Let's think about it this way. Think about it with a number that we know better, a dozen. If you had a dozen lithium carbonates, how many carbon atoms would you have? All right, if you had 1 lithium carbonate, how many carbon atoms would you have? Just 1, because that's what the formula tells us. There's just 1 carbon per formula unit. So if you had a dozen lithium carbonates, how many carbons would you have? 12, or you could say a dozen. If you had a mole of lithium atoms, or of lithium carbonate, how many carbon atoms would you have? Or how many moles of carbon atoms would you have? Everybody sort of froze there, but it's the same thing. So it's still 1. So the formula tells us that there is 1 carbon atom per each lithium carbonate. That's what the subscript, the fact that there's no subscript, tells us. We could also say for this particular compound that there's 2 lithiums per each lithium carbonate. We could also say there's 3 oxygen per each lithium carbonate. And I didn't put any units in there for a reason, because those units could be various different things. We could say individual ones, like formula units. We could say dozens. We could say moles. It works for all of those. So if we jump over to the middle one, the lithium one. If we have 1 formula unit of lithium carbonate, we have 2 lithium atoms. That's what the formula tells us. If we have a dozen lithium carbonates, how many lithiums do we have? 24. Because we've always got, or we could say 2 dozen if we don't want to actually count it all out. We could say 2 dozen lithium carbonate, or lithium atoms per dozen lithium carbonates. Because we're always going to have twice as many, because the formula tells us it's 2 to 1. If we jump over to the oxygen, same thing. If we have a dozen lithium carbonates, we're going to have 3 dozen oxygens. And so don't get messed up when we switch that word to mole. It still means the same thing. Once you have the ratio from the formula, everything else is the same. So we can say that in every 1 mole of lithium carbonate, we'd have 3 moles of oxygen. So let's answer the question then. If we have 1.5 moles of lithium carbonate, that's what the question tells us we have, we want to multiply that something that gets us from moles of lithium carbonate to moles of just carbon. And those equivalences that we just came up with are what we're going to use there. So we've got 1 of these for every 1 of these. So that's the first step here. For every 1.5 moles of lithium carbonate, we have 1.5 moles of carbon, because it's 1 to 1. There's 1 carbon per each lithium carbonate formula unit. But that's not quite what the question asks yet, because the question asks how many carbon atoms. It doesn't say how many moles of carbon. It says how many carbon atoms. So that's when we have to use that big number. And do another conversion from moles of C to atoms. But the good news is this. It's always the same number when you go from moles to individual atoms. So if you have a mole of carbon, then you're going to have 6.02 times 10 to the 23rd atoms of carbon. So 1.5 moles of lithium carbonate gives you 1.5 times that number atoms of carbon. All right, so let's talk a little bit about how to deal with that big number with calculators, especially calculators that don't have scientific notation on them. So here's what you do. I just realized there's a whole box of calculators here, so I use one of these. So does anybody have a graphing calculator? Because I can show you that too, because it's a little fancier. Does anybody have one here? No? Okay, we won't worry about that. All right, so here's my little calculator, and I want to know how to do 1.5 times 6.02 times 10 to the 23rd. So, 6 with 23 zeros behind it. I can't fit 23 zeros on the screen here, so that's not, typing it in directly is not a good way to go. So what do I do instead? Anybody know? You can actually just multiply or divide or whatever you need to do the rest of it, and then just stick the times 10 to the 23rd onto the end. So for this particular problem, I just go 1.5 times 6, or 6.02, or whatever. And so my answer would be 9.03 times 10 to the 23rd. And I don't even have to mess with that. That's atoms of carbon. It's true that if your number goes above 10 or below 1, you're supposed to correct the little exponent. And so like if you were 10 times 10 to the 23, that should really become 1 times 10 to the 24. But for this class, we're not going to worry about that. If you know scientific notation, or if you're doing it on a graphing calculator and you want to make those corrections, go ahead. But for me, it's good enough if you just multiply the numbers and stick the times 10 to the 23rd on the end. All right. So there's a lot of good practice problems on this kind of stuff in the book. Make sure you can check the Blackboard also for the list of stuff you want to be able to do. I think that's about halfway. So let's take a break here. When we come back, we're going to do some more practice problems. I know that was kind of a new thing, so I want to make sure that you get some chance to practice it, and then we'll move on from there. All right, so I'll see you in about 15 minutes. All right, so let's go on. During the break, some of you probably heard us talking about this number here has a name called Avogadro's number. I don't think that's really important to know that that's its name, but that's what its name is. It's in the book. So the main point of that number is, again, to convert us, or to allow us to convert from the molecular scale of these tiny things to a scale that we can actually understand and measure and deal with, which is the mole scale. So let's do a few more practice problems here of some different types that you'll see in the book and on the quiz next week, dealing with this idea of moles and converting between these two scales, atoms, molecules, and moles. So let's just stick with one unit at a time. So we're going to calculate the mass of 0.25 moles of phosphorus, 3.5 moles of C6H6, okay, so we'll try those two. We'll do the first one together, and you can try the next one. So if we want to know the mass of 0.25 moles, we can think of this as a conversion type problem, just like from chapter 2, where we're setting up a plan. We're going from moles, which is given, to grams. So in order to do that, we need a conversion factor. Our conversion factor in this case is that molar mass. How many grams are in 1 mole? So for the first one, we would say, all right, 0.25 moles of phosphorus. And I want to go from moles of phosphorus to grams of phosphorus. So then I need a quantity that tells us how many grams of phosphorus are in a certain number of moles, and I get that from the periodic table. So that's that number, and we'll just stick to whole numbers here, 2 significant figures. So 31 grams per mole is what the periodic table tells us. And now I do have a calculator, so 0.25 times 31. 7.75, or we could just say 7.8. So if we wanted specifically 0.25 moles or a quarter mole of phosphorus, that means that we would need to weigh out 7.8 grams of phosphorus. Okay, so see if you can do the next one. Same type of question, different compound, different numbers. How many grams would you need for 3.5 moles of C6H6, which is a compound called benzene? All right, so what are the basic steps here? What do you do first?
Check the weight of carbon and the weight of hydrogen.
Yeah, we're gonna have to, this time, the difference from the previous one, we're gonna have to add up all those masses together, the carbon masses and the hydrogen masses, so that we get the molar mass of the whole compound. So we can do that first, or we can set the whole thing up and do it later. Let's set the whole thing up since we're trying to do it the same way again. So we want to ask that same question, 3.5 moles of C6H6 is how many grams? So we need that same kind of a quantity that we had before. This time, we can't just look up and copy the number directly from the periodic table. We have to add it up and get the molar mass of the whole compound. So that's 6 carbons. 6 times 12 is 72. And then 6 hydrogens, that's 6 more, 78. So that's going to be 78 grams per mole. Which comes out to 273 grams. Is that right? Maybe check it. I don't know. Some people remember it looks. Okay. All right, so that's one way we could do it. We could be given a certain amount of moles and then calculate the amount of grams. We can also do it the other way. Same exact thing. We just flip the ratio. So let's try one. Let's just ask it this way. How many moles of carbon are in 75 grams of carbon? And then to review from before, also how many moles of C are in 0.25 moles of C2H6? I would encourage you, I mean, if you want to take shortcuts, that's fine if they work for you, but I would encourage you to think of these all as the same type of problem. You have to convert your units from one to the other, just like we did in chapter 2, because that way it keeps it all constant. If you find better ways of doing it, that's great, but we can actually do it using that same technique all the way through. So we can say in this first one, for instance, we're going to go from grams of carbon to moles of carbon, and then set up our equation in that way. So we go 75 grams of carbon, and then we want a quantity that gives us grams of carbon to moles of carbon. The thing that relates grams and moles is the molar mass. So we look up on the periodic table, since it's just one element, one atom. We see carbon is 12, and this is the only kind of tricky thing, not really tricky, but we got to remember the 12 goes with the grams. It's 12 grams per mole. So the 12 grams goes here, the mole goes here. We calculate that by dividing 75 by 12. We get 6.3. And so now that's moles of carbon. So in 75 grams of carbon, that's 6.3 moles of carbon. And then the second question is a little bit different, because we're not going grams of something to moles of something. We're going moles of something to moles of something else. So in this case, we're not going to calculate a molar mass because there's no grams involved. And that's something that is a common mistake when you see problems like this. How many moles of carbon are in 0.25 moles of C2H6? That's moles to moles. There's no grams involved there. So we're not going to use any kind of molar mass. So in this case, we're converting from moles of C2H6 to moles of just carbon. So you could maybe just see that and know how you're going to convert that. But we can set it up in an equation anyway, just to make sure we know what we're doing here. So in this case, we'd go 0.25 moles C2H6. And we want a quantity that relates moles of C2H6 to moles of just C. How do we find that? How do we find the relationship between moles of C2H6 and moles of just C? We can think of it as kind of like a sentence or a question. How many moles of carbon are in a mole of C2H6? 2, right. That's the questions that we answered earlier. The formula tells us that. The formula tells us that right there. That little C2 tells us that we've got 2 moles of carbon for every 1 mole of C2H6. So that means that the answer to this question is going to be there are 5 moles of carbon in a quarter, or 0.5 moles of carbon in 0.25 moles of C2H6. All right, let's extend these calculations then to some of the equations that we've just been dealing with. I'm going to copy one of these down here just so we can use it. We've been dealing with that middle one, so we'll just continue to do that. 2 CH4O plus 3 O2 Sure. That? Or? Yeah. I didn't forget about it. But the question wasn't asking that. So the question's asking how many moles of just C. So that's why we just want to know about the C. Yep. Yeah, thanks for asking. So we talked about how these equations mean that these are going to react in a particular ratio. If you have 2 of these, then you have to have 3 of these to react with it, and then you're going to make 2 of these and 4 of these. So that's those coefficients. The reason we balance the equation to make sure that the masses are balanced, and so we can use these coefficients to figure out how much of each thing we need. So this works with moles too, because we can, as we said, we can say those numbers with moles just like we say them as numbers or dozens or however you want to do that. It means you can use that in the same way. It doesn't quite mean the same thing, but we can use that in the same way. So the way that we can ask about this is something like, how many moles of oxygen are needed to react with 1.7 moles of CH4O. That's a question mark. How many moles of O2 are needed to react? So you have some certain amount of CH4O that you want to react with. You need a certain amount of oxygen to do that. But we can use the ratio from the equation to figure that out, because what the equation tells us is kind of like conversion factors again. It tells us that there are 2 CH4Os for each 3 O2s, or upside down, 3 O2s per 2 CH4O. We can use those relationships from the equation just like we use those relationships inside formulas. Like we said that there are 4 H's in every CH4O. We can say that there's 3 O2s in every for every 2 CH4Os. That's just what the coefficients in the equation tell us. That's a ratio. It's the ratio by which they react. So to answer this question, we can set it up like a regular conversion type question where we say there's 1.7 moles of CH4O. And we want a factor that tells us the ratio between moles of CH4O and moles of O2. Remember, in these types of conversion problems, we're always going from the thing that we're given to the thing that we want. So the thing that we're given here is moles of CH4O. The thing that we want is the moles of O2. And the thing that gives us the relationship between those is the numbers directly from the equation. So it tells us there's 3 of these for 2 of those. That 3 and the 2, we make a big mess here, but come directly from the equation. So then we can evaluate that. 1.7 times 3 divided by 2 and get 2.6 moles of O2. So in this way, we can always figure out how much of another quantity we need. And this is not just useful in chemical equations. This happens in a lot of different times. We have different kinds of ingredients that you need to have in certain ratios. I was making pancakes the other day, and the pancake mix was like half empty. So there was only, I weighed it, there was like 300 grams left or something. So then I had to figure out how many eggs and whatever oil I needed that was different from the recipe, so you can use that same ratio. If it's 200 grams of pancake mix per 2 tablespoons of oil, then if I had 300 grams, it would be 3 tablespoons of oil. You can use those same ratios to try to adjust things. And this comes up in medicine and things like that as well, when you're looking at different ratios and trying to figure out if you have so many of one, how many of the other one do you need? All right, so let's try this in a kind of an overall problem of how you would do kind of a whole thing of this on an exam or something like that. I'm going to type this just so it doesn't get messed up again. All right. Lead 2 nitrate reacts to sodium chloride to form lead 2 chloride precipitate and sodium nitrate. Excuse me. How many moles of I'm going to change that. Sorry. How many moles of lead 2 nitrate needed to precipitate 0.3 moles of lead 2 chloride? So this is an example of what might happen like in the lab. You'd be reacting some stuff together, and you have a basic idea of what that reaction does. You know how much product you want to make, so you have to figure out how much you want to start with in order to make that amount of product. It may be 1-to-1. It may be that you just use the same amount that you want to end up with. We won't know that until we actually build the balanced equation. So take a few minutes, work together with other people at your table if you want, see if you can build the balanced equation for this reaction, and then figure out how many moles of lead nitrate you need to precipitate 2.3 moles of the lead 2. You need to put together the balanced equation. It's not worth trying to calculate stuff. So you've got that equation because you don't know what your compounds are, what you need exactly. I don't want to interrupt your great equationing, but I'm going to write the equation up here so you can check that, and then at least continue on with the rest of the problem if you're having trouble putting the equation together. So check your equation, note where it may be different, what the issues were, and see if that last for the problem. All right, sorry to rush you, but we should keep going. So do you need to calculate molar masses for any of these compounds in this problem? What do you think? To figure that out, we have to look at the problem and what it's asking. So the question here is, how many moles of lead nitrate are needed for 2.3 moles of lead chloride? So what the question is asking is, given a certain amount of moles of lead chloride, how many moles of lead nitrate are needed? To figure out that relationship, we don't need any molar masses because we're not talking about grams, we're just talking about moles. So we just need those numbers from the equation to get that ratio. That looks like this. So we'd go 2.3 moles of lead 2 chloride. And then we need a quantity that gets us from moles of lead chloride to moles of lead nitrate. And to do that, we just take the numbers directly from the equation. In this case, it's 1 to 1. If there's no coefficient out in front in an equation, that's because it's 1. So it's 1 to 1, and therefore the answer is also 2.3 moles of lead nitrate. But that took a lot of work. It takes a lot of kind of all the stuff we've been building on for the last couple of weeks to get to there, because we had to first put the compounds together properly, then get the equation balanced properly, and then finally put that extra piece in from today where we do a mole-to-mole conversion, where we go from moles of one compound to moles of the other compound. So when you're doing problems like this in your homework, make sure that you're practicing those individual steps and figure out where your issue is. Is it making the compounds? Is it balancing the equation? Is it doing the mole-to-mole conversions? There's practice problems for each of those things throughout the chapter. One is putting the compounds together is back in chapter 6, but the other stuff is all chapter 7. So make sure you take a look at those. We are going to skip one part of chapter 7. Sorry. Which is 7.7. It's the mass calculations for reactions. So how to do the same kind of thing, but with grams instead of moles. It puts an extra step in there. It's not that hard, but it's just not something that's in the objectives for this class. So we're not going to do that part. The rest of today is a little bit more descriptive. We're going to look at the types of reactions. And we'll be doing this in lab on Wednesday also. So how do we determine what kind of reaction is happening? And the reason that's useful is it allows us to make predictions. Once we know what the type of reaction is that we're looking at, we know, or we can guess what the products are going to be and actually have a pretty decent guess. So let's take a look at those. Now there's tons and tons of different chemical reactions, of course. They don't all fit neatly into these categories, but the ones that we're seeing mostly will, and all the ones that we're doing on Wednesday and next week in lab will. And it's a really powerful predictive tool if you have reactions that fit into the category. So let's take a look at them. For each of these types, I'm going to give you the name. So this one's combination. I'm going to give you a kind of a generic formula for what that looks like, and then a specific example. A combination reaction is one where you have two or more reactants that just combine into one product. So I'm not talking about this. There is no element A. I'm just saying in general, you've got two things that go together. For a specific example, if you take solid magnesium and you react it with oxygen, which means you burn it, you make magnesium oxide. And so you can see how that's a combination. You've got two different reactants, and then in the product, they're just kind of squished together. And you can also kind of see how that's predictive if you know something's, or you suspect something's going to be a combination reaction. If I tell you, okay, these things react via a combination reaction, and you've got two different things, then you just have to make a compound between them. How do you know that the product would be MgO and not MgO2? It's a combination reaction. Why does it have to be MgO?
Because there's two, like with the 2 in front of the Mg, and then there's, so that automatically means everything needs 2, like each.
Sure, yeah, but let's say we didn't have the balanced equation, and I just said magnesium and oxygen react together in a combination reaction. How would you know to make the product MgO and not MgO2? In this case, you could use your rules of ions, because that's an ionic compound. We know magnesium is +2, and we know oxide is -2. So the compound between magnesium and oxygen is always just going to be MgO, +2 and -2. So we can bring together all that information, all that knowledge from before to help build these things. All right, that's combination reactions. Kind of the opposite of that is called decomposition. It's where you have one thing that's made out of multiple atoms, so a compound, and it breaks apart. It doesn't always break apart into its constituent atoms, but it just breaks apart into two pieces. An example is one we're going to do on Wednesday. Solid calcium carbonate decomposes into calcium oxide and carbon dioxide. So you have a compound, the pieces of that compound break apart. These are really hard or sometimes impossible to predict, because how do you know which parts of the compound stick together when they break apart? You don't always know. Like, why did it have to be CaO and CO2? It could have just been Ca and CO2. You know, or it could have been Ca and CO, carbon monoxide. So those are really hard to predict because you don't know exactly what ratios of things are going together necessarily. I think I could probably fit this here. Our third kind of reactions are going to be substitution reactions. Substitution reactions, there's two different kinds. There is what we call single replacement. And then there's going to be double replacement. We'll look at them one by one. So in single replacement, you have a compound reacting with an element. And then in the product, the element has replaced one of the pieces of the compound, and the other one ends up by itself. There's one example of this on the board right here. This one. So you've got aluminum by itself, and then you've got these two together. In the products, aluminum ends up replacing the cobalt, the compound, and the cobalt's off by itself. The one we're going to do on Wednesday looks something like this. You can take HCl and zinc. And that involves hydrogen gas. So in this case, the zinc is replacing the hydrogen to make a compound with the chloride, and the hydrogen gas is leaving. Notice that in some of these, we can predict it by switching the places, but we have to re-switch the subscripts because the subscripts have to be for the compound that that they're a part of. So like the HCl has got one H and one Cl, but ZnCl2 because zinc makes a +2 ion. You may not know that one for zinc specifically, but if we were doing one like aluminum that we knew, we'd know that aluminum would have to switch so that you have 3 nitrates because it's +3. And then the double replacement is similar. Yeah, computer's getting angry tonight. And now you've got two compounds. And they're going to switch. And these are generally ionic reactions. So you've got ionic reactants, cation and anion, switching places. So the cation goes with the other anion. So like A, let's say A is the cation because we usually list that first, the positive one. So that would go with the negative ion from the other one, which we might say is D, and then CB. And these are the common like precipitation reactions that you actually saw some of last week, and we're going to do more of this week. For example, I think this is when we're going to do cobalt-2 nitrate reacts with sodium hydroxide. And so then the cobalt ends up with the hydroxide, and the sodium ends up with the nitrate. In this case, the cobalt hydroxide is the precipitate, the little solid thing. You'll see this on Wednesday when we actually do it. All right, so those are three major, I guess four, I don't know, however you want to call that, types of reactions. There's one more. And that is combustion. In a combustion reaction, we have it doesn't really have a kind of a generic thing, but you have some kind of a hydrocarbon. So if we wanted to be generic, we could say something like this, some kind of compound made of carbon, hydrogen, oxygen, so these kinds of things. With any ratio of those, that's why X, Y, and Z. And that's reacting with oxygen gas. To form carbon dioxide and water. And usually a large amount of energy too, so exothermic reaction. So the nice thing about this is it's not as like variable as the other ones. It's always reaction with oxygen, and your products are always just carbon dioxide and water. It doesn't matter what you start with. So any hydrocarbon plus oxygen in a combustion reaction, you could draw the product for really easily. It's always the same. All right. So now that we know those categories, let's try a couple and think about how we could potentially predict the products based on what we see in the reaction. So let's say this one. So we've got iron oxide, which is rust, plus solid carbon. That should be solid also, the FeO2, or Fe2O3. So if you look at this reaction, you go back through those categories, what does it look like? Which form does this most resemble? And with this kind of a thing, it's really not absolute. The only way you can absolutely categorize these reactions is if you see both sides. Only seeing one side is kind of a guess of which category you think it fits in the best. You could probably make an argument for a couple here, but there's one that it really fits best. So what do you think? Which one would you go with?
Single replacement.
Single replacement? Why?
Because just looking at the chart, it's like that carbon can replace iron pretty easily with the oxygen.
Sure. So we might look at this and say, yeah, one compound has two things in it, and then there's one thing by itself. So that kind of looks like single replacement. So we might say the carbon's going to replace one of those other elements. Now, how do we know if the carbon replaces the iron or the oxygen? Would you make a carbon-oxygen compound or an iron-carbon compound? Why? Sounds better? Yeah, I mean, that's the thing, is that, like, there's not really a good answer there. There's not a good way to know that, except to think about what are some common compounds that you know, and what seems like most likely. But even that, it's not great. But so let me just tell you the answer, and then we'll see how that worked with what you would have put. So the answer is that these form CO2 gas and iron solid. And then we've got to balance it here. So we've got to go 2, 3, that. So we were right that it was a single replacement reaction. And the carbon ends up replacing the iron in this case. We weren't necessarily right about that because we thought maybe that carbon would replace the oxygen and oxygen gas would come out. And if it does replace the iron, we might have been able to predict that it makes CO2 because that's kind of the most common compound of carbon and oxygen. The most stable is carbon dioxide. But there's really no right answer here. If you just saw those first two, you'd be making guesses as to what came out. So how does that work in an exam type situation? You just either get lucky or lose all the points? There's a couple ways that I could ask about this. So one is I could leave it open-ended and ask you to write about why you picked what you picked, with the expectation that whether or not you'd be right, you'd be graded on your justification. You could also do this in like a multiple choice question. So you could say, all right, what are the products likely to be? And just don't give ones like iron and carbon compounds as choices. So that only your choice, like that's the only choice for a single replacement reaction. That kind of a thing. But it is really tough to predict reactions. Let me show you when you can predict it pretty reliably. The last two ones we talked about, you can predict reliably. The double replacement and the combustion. So let's look at one of those. Find one. So if I said, predict the products of this reaction, you could see this as what? What type of reaction is this? This is double replacement. How do we know it's double replacement? Yeah. Yeah, so you've got, I mean, there's lots of different, there's more than 4 elements, but the key thing is 2 ionic compounds reacting. There's very few situations where you're going to have 2 ionic compounds that do something else together. And usually, if they're going to react, it's usually because they're switching ions. So if we want to switch ions on these, we can do that, but we have to make new compounds. So you can't just say, oh, the K2 goes with the NO32 and the PB goes with the S. You have to build new compounds. What would those new compounds look like? And to do that, we need to look at the ions. So in this case, we've got K2S is made of K plus and S2 minus. PbNO32 is made from lead 2 plus and NO3 minus. So if we now make a new compound that connects the lead with the sulfide and the potassium with the nitrate, 2 new compounds, we're going to balance out those new charges too. So we've got PbS, those are going to be 1 to 1 because 2 plus 2 minus, and KNO3. Then we'd need to balance that. So we put a 2 here. So in this way, we're able. So with those double replacement reactions, we're able to predict it. We can switch the ions and make new compounds from the switched ions. All right. We'll try this more on Wednesday. So the last thing we're going to talk about is oxidation reduction reactions. We're not going to get quite as much into it as you may have before. They're not their own separate type of reaction in the list of the ones we did before, because it applies to all those other ones. Those other reactions can also be oxidation reduction reactions. We can think of oxidation and reduction as a change of charge. It's not really charge. It's something different called oxidation state. But for our purposes, we can think of it as a reaction where one of the elements changes its charge. And the primary way that you identify oxidation reduction reactions is when you change from an element. So I guess we can get, I don't want to get too deep in this because it's not something that's going to come up a lot in this class. But what these words mean are transferring electrons. So oxidation is when something loses electrons. Reduction is when something gains electrons. So for instance, if you had something that went from, let's say, potassium goes to K+, that would be considered an oxidation reduction or an oxidation process because it's lost an electron. The opposite, reduction, gains electrons. So for instance, if you had Cl2 and then you end up with minus. What's the charge on an element that's all by itself in its elemental state, like O2 or C or Al? If an element is just by itself, what's its charge? Neutral, it's 0. So if you have a reaction that you have a neutral element that then becomes part of a compound later, that's your key that there's oxidation or reduction going on. So let's look at an example from the board here. Well, no, that's not a great example. Let's look at the bottom one. The bottom one's a good example. So you've got aluminum reacting with this compound, cobalt nitrate. So one thing we could do is ask, is this reaction an oxidation reduction reaction, sometimes called redox? Is this a redox reaction? The way we figure that out is we look at the charges on the metals, because those are usually the ones that are changing the charge in these types of reactions, and we see if they're changing their charges. So we look at aluminum, for instance. What's aluminum's charge on the left of this reaction? We just said it earlier. It's neutral, so it's 0. So on the left, it has a charge of 0. What's aluminum's charge on the right? In that compound, in that aluminum nitrate compound, what's the charge of aluminum? Well, it's positive something. what is aluminum's charge always when it's in a compound? +3. It's always +3. So in this compound, it's also +3. We can also figure that out by the fact that there's 3 nitrates with it. Nitrates -1. So it's got to be +3 to balance that. So in this case, in this reaction, aluminum has gone from 0 to +3. Does that mean that it has lost electrons or gained electrons? Lost, right? Because it went from neutral to positive. Electrons are negative. So if it loses electrons, it's gone positive. And that's what we call oxidation. It lost electrons. Similarly, what is the charge of cobalt on the left? +2, yeah. That's one that we can't get from the periodic table, but we can look at nitrate and say each nitrate has to be -1. There's 2 nitrates, so cobalt's got to be +2 to balance that out. And then what's the charge of cobalt over on the right? On the right of this particular reaction. Why? Oh, yeah, that's the coefficient, though. That's not going to affect the charge. I was wondering, cobalt's all by itself in the compound. So if something's all by itself, what's its charge? Always. It's always 0, yeah. Always neutral if it's by itself. So cobalt went from +2 to 0. Is that a gain or a loss of electrons? That's a gain, because it was positive, so it gained some negative electrons to become neutral. So that's what we call reduction. So here's an example of an oxidation-reduction reaction. So we can look at reactions and determine this based on the charges and the change of charges over the course of the reaction. Most of these reactions, I'm looking at the book here, and I think it's really all of them that they're showing you. The key to look for is to try to find neutral elements. If you have a reaction where something is all by itself on one side, then it's virtually certain that that's going to be an oxidation-reduction reaction. That's your clue to look for that. So single replacement reactions, a lot of those are oxidation-reduction reactions. Combination, same thing. If you've got 2 things that are by themselves and they come together, that's oxidation and reduction. Double replacements, usually not. Usually they're switching, but the charges are staying the same. If we look back up here at our double replacement reaction that we just looked at, so K is +1 on the left, +1 on the right. Lead is +2 on the left, +2 on the right. Doesn't change its charge. So that's not oxidation reduction. No electrons have changed. Only the ions have moved. All right. Everybody looks really tired. Yeah, okay. Okay. We're almost there. We're almost there. Very last thing of the night. We want to look at what we call a reaction coordinate diagram. It's kind of like the heating curves that we saw before. In this case, we're plotting reaction progress versus energy. So we're saying the reaction starts on the left and goes to the right. So what happens as you move these things, as you mix these things together? What happens to the energy of the system? So here's an example of what one of these might look like. I'll talk about what that means. What this tells you is the reactants are over here, and the products are over here, because that's that left to right thing. That's what that x-axis means, reaction progress, going from reactants to products. And what happens to the energy? Well, it starts where it starts, and then it goes up, and then it goes down. So a couple of things this tells us. First, the difference in energy between the reactants and the products is what we call the heat of reaction. In this case, the heat goes down. So the energy was up here and it goes down here, which means what happened to that energy? If the energy level was 100 and now it's 5, what happened to the rest of the energy? It's released. So this is an example of an exothermic reaction. The fact that the products are lower in energy than the reactants tells us that this particular reaction is exothermic because the heat is released. What would an endothermic reaction coordinate look like? How would it look different from this one? Yeah, the products would be higher than the reactants. So instead of being like this, they'd be like this. All right, so now let's deal with that hump in the middle. What's going on with that? Why don't the reactants just go down to the products? Idiot, what? So let me give you an example. Let's say a combustion reaction. Anybody like burning stuff? Have you ever burned some stuff? So you have gasoline, let's say. Gasoline sits in the earth forever, for millions and millions of years. But when gasoline combusts, it releases a huge amount of energy. So it's the combustion reaction is highly exothermic, and yet it doesn't happen until what? What do you have to do to start a combustion reaction? Yeah, you have to ignite it. You have to give it energy to start. And that's what that first hump is. That's called the activation energy. And that's the amount of energy required to start the reaction up. Once the reaction gets going, if it's exothermic, it's making its own energy to keep it going. But at first, it needs that start. It needs that spark, that energy to get started. And in a lot of cases, that barrier is enough to stop the reaction from happening. And so it can be difficult to get your reaction going. So one thing that we can use for that is something called a catalyst. And that's a word that we use a lot in non-chemical conversation and writing and things like that. What does it mean? Yeah, it's something that kind of speeds things up. And it does speed up the reaction, but it does it in a particular way. It lowers that activation energy. So we talk about enzymes in the body. Enzymes are catalysts for biological reactions. The biological reactions in our body wouldn't happen because their activation barriers are too high. But when there's catalysts around, when there's enzymes around, they can change the mechanism of those reactions and allow them to happen at a lower energy level. And that way it speeds it up. So we often say that it's about speeding it up, but really what it's about is lowering the activation energy. This also tells us that there are some other ways to speed up reactions too. So how else do you speed up a reaction besides a catalyst? You didn't have a catalyst. Ideas? No, it's late. Sorry.
Changing temperature.
You could change the temperature, higher or lower. Which do you think speeds up the reaction? Higher, yeah. You give it more energy. It has more energy to get over that barrier, so it's going to go faster. And then another one is you can change the concentration. So you could change the amount of reactants you have. If you increase the concentration, do you think that speeds up the reaction or slows it down? You want to make a guess on that one? It speeds it up, yeah. Remember, chemical reactions only occur when molecules bump into each other. And bump into each other just right. So the more of them you have, the faster they're moving, that's temperature, the more collisions you have, and the more you're going to get the reaction sped up. So you can speed up the reaction by catalyst, by increasing the temperature, by changing the concentration. Okay, that's reactions. Feel like this was fun? No?
So much fun.
Okay, good. I appreciate your totally not sarcastic enthusiasm. All right, so Wednesday we're going to do a bunch of chemical reactions. Hopefully you'll see more of this stuff in action. And then on Monday we'll do another quiz focusing on these mole calculations and types of reactions and stuff we've been talking about tonight. So happy homeworking, and I'll see you on Wednesday.
Do you mind putting it up to the oxidation reduction part?
Sure. That is also section in the book. It's in section, find it, 7.5, oxidation reduction reaction.